All right, here's an example of an angular motion problem. We have a 3 centimeter diameter crankshaft is rotating at 2,500 revolutions per minute, and it comes to a halt in 1.5 seconds. What is this angular acceleration and tangential acceleration? Okay? So angular acceleration, remember, is alpha. So we're trying to find alpha, and we're trying to find AT. Once we get alpha over here, we can get AT. Actually, I messed that up. Sorry. It's alpha tangential, A tangential is equal to alpha r. So these are our angular acceleration equations over here. All right, figure out alpha. We know what its initial velocity is here. Omega initial is equal to 2,500 revolutions per minute. However, remember I told you that these equations up here, just for ease of doing it, convert them always to radians per second. Okay, velocity should always be in radians per second. If you don't, you're going to get in trouble, because the revolutions per minute gets complicated, especially when you start having alpha in here, because then you get in revolutions per minute squared, and then you can't use this conversion over here too. This only works if you're in radians, remember. So just convert it to radians per second. So to convert this, I'm going to put 1 minute on the top is equal to 60 seconds on the bottom. And on the bottom, I'm going to put 1 revolution is equal to 2 pi radians. So what I'm going to do is take 2,500 times 2 pi and then divide that by 60, and I get the initial velocity. And when I do that, I get the initial velocity is 261.8 radians per second. Now the final velocity, it says to a halt, so the final velocity is just 0. And I know how long it took, so I'm just going to use this equation right here. Omega equals omega naught plus alpha t. Or alpha is equal to omega minus omega naught over t. Or in this case, we have 0 minus 261.8 all divided by 1.5. And when you do that, you get minus 174.5 radians per second squared. Notice it's negative. Well, it has to be going the opposite direction of the velocity. It didn't tell us which way the velocity was rotating, so we just made this positive. Well, then alpha has to be negative to slow it down. They have to have opposite signs. Okay? But that's only part of it. So we figured out the angular acceleration. Now I want to know the tangential. Well, the tangential acceleration is just equal to alpha r. Or in our case, alpha we have, it's minus 174.5. And the radius, remember, is half of this, but we need this to be in meters. So this is 0.015 meters. Because it's half of this, which is 1.5 centimeters. And then you have to move the decimal over 2 places to put it into meters. When you do that, you get the tangential acceleration is minus 2.6 meters per second squared. And I also went down to 2 sig figs because that's all we have. All right, how many revolutions does the crankshaft make? Well, in this one we need to figure out what theta is. We could either use the top equation or we could use the bottom equation, because we have everything else in here. I'm going to use the bottom one, but it would work just as well on the top. So we're going to say omega squared equals omega naught squared plus 2 alpha theta minus theta naught. Well, originally we're going to call that 0, so all we're looking for is theta. So I'm going to solve this for theta. When I do that, I move that over there, so this becomes omega squared minus omega naught squared, all divided by 2 alpha. Gives us the answer. So, omega is 0 minus 261.8 squared over 2 times negative 174.5. And when you do that, you get theta is equal to 196 radians But they didn't ask for it in radians, it asked for it in how many revolutions, so I have to convert. But remember, I'm going to put 2 pi radians on the bottom, 1 revolution on the top. The radians will cancel. And so all I have to do is do 196 divided by 2 pi. And that's equal to 31 revolutions. And if I could write, we would have it. There we go, 31 revolutions. All right, so these are our answers here. That. And that's how you do these problems. Most of it is just figuring out which equations to use at the different times.